Hello everyone, today the theme I'm sharing with you is discuss the degradation mechanism of Tiger Neo modules. Briefly, my presentation is into two main sections. And firstly, I will provide a general introduction of PV panel degradation. The degradation is defined as a series of mechanisms through which a PV module degrades and reduces its output power year after year. The rate is the most direct indictor, which is the ratio between the degradation power and the initial PV power. During the full year of 30 years, PV modules will degrade due to various reasons, which is not caused by a single isolated reason, but by several degradation mechanisms affecting PV modules. These causes of solar panel degradation including LID, LEPID, LETID, PID, UVID, and agent. Let us analyze them in more detail. Above all, we will discuss with LID and LETID. Light-induced degradation is an output power degradation of PV modules or solar cells caused by illumination, affecting modules mainly during the first year of operation. The degradation mechanism of LID is due to traces of oxygen, including in the silicon, during the Jinko process. And under the line, this positive charged oxygen may diffuse across the silicon lattice. The boron-oxygen complexes create their own energy levels in the silicon lattice and can capture electrons and holes which are lost of the PV effect. As shown in the right picture, boron-oxygen formation leads to a strong efficient degradation for the Jinko monocrystallized silicon cell, which is the purple star line. For all multicrystalline silicon cells, the efficiency degradation is quite small. This is to say, LID of P-type monocrystalline PERC cells in more series is more series than conventional crystalline cells. However, N-type cell uses phosphorus-doped silicon wafers as a substrate, so there are fewer P-type in the P-N junction, so there are fewer boron-oxygen complexes because LID has no significant impact on the N-type cell. The light and elevated temperature induced degradation was accelerated by increasing temperature and illumination, as shown in the right picture. Compared to the traditional multicrystalline cells, monocrystalline PERC cells exhibit survival power degradation at 75 Celsius degrees, but power output will gradually regenerate with increasing temperature and time. There is no mature theory about the degradation mechanism of LETID. Different scholars have different views about the mechanism. At present, there are two root causes supported by the theory and data. Hydrogen or metallic impurities induced degradation. For HID, hydrogen atoms in anti-refraction films diffuse into the silicon. Hydrogen ions tend to neutralize and bind with the dopants, for example, through forming neutral boron-hydrogen species. As for MID, metallic impurities may be introduced by raw material and process, and recombination centers are formed under high temperature activation. PID is one of the important problems which we should focus on. When the module's voltage potential and the leakage current drive ion mobility within the module, a large amount of ions accumulate on the solar cell surface. This causes a strong reduction of the surface passivation and lead to a power output degradation. In standard crystalline silicon PV modules, leakage currents can flow from the module frame to the solar cells along 6 different pathways, which are depicted in the right picture. For example, the first way is along the surface of the front glass and through the glass and the encapsulant. Similarly, there are also different routes of the PID. The first is about PID shutting. The module frame should be grounded, and so a high electric potential difference often exists. Sodium ion drift through the air coating towards the interface and penetrate into crystalline defects, crossing the heavily doped NP junction. This results in significant shutting of the cells and degrades their efficiency. About PID polarization, when a cell is subjected to a high positive potential, current leakages from the cell through the encapsulant, which causes negative charge accumulating on the surface of the silicon nitride air coating. Therefore, instead of being collected by the cell's p junction, light-generated holes in the front region of the cell are more attracted to the front surface of the cell by the negative charge in the AR protein, which are where they are recombined with electrons. This results in increased surface recombination. Typically, a cross-F PIDC can occur below the silicon-natured AR protein and alumina passivation layer. About the first corrosion route, the cation impurities in PV modules can pass through the encapsulant, forming silicon or oxygen cracks, leading to depassivation effects. Another route is that there are cross-F byproducts in the production and application of PV modules. These cross-F chemical components can react with the metal electrodes by armed solar cells, resulting in permanent output power degradation. In brief, PIDs can occur or can affect AR coating and passivation layers. PIDP can affect AR coating, and while PIDC mainly affects encapsulant and accelerate the impact of PIDs. Therefore, as shown in the picture, for an N-type cell, the front is prone to phenomena of PID shutting, polarization, and corrosion. The back is prone to the phenomena of PID shutting and corrosion. UVID is quite new story about degradation. Some articles have shown that UV photons have shallow penetration depth in the cells and can penetrate the encapsulant. This detrimentally affects the module's performance and durability, increasing interface effect. In the past, UV degradation mechanism of PV modules was primarily observed as the discoloration effect of the encapsulant. But as shown in the right picture, a previous study found that modules featuring with an alumina heavily doped p-type silicon passivation cell front side are stable under UV exposure. In contrast, irradiating modules featuring with an amorphous silicon nitride heavily doped N-type silicon passivation reduces the output power by 15%. Finally, aging is also the main degradation affecting PV modules. It's a long-term degradation mechanism affecting output power of PV modules. The main reason is related to the degradation of encapsulant and solar cells. This degradation mechanism is a direct consequence of modules being exposed for years of rainfall, snowfall, and other external agents. When PV modules are exposed to the aforementioned external agents, they start to decay over time and reduces their efficiencies. This occurs by solar panel frames corroding, glass and backsheet delamination, and regions of the encapsulant causing the decreases of light transmittance. And then we will talk about test method and cases. For this PV module degradation, the IEC also defines the corresponding test methods. The LID test consists of a series of light exposure intervals of equal irradiance above 5 kWh per square meter. However, based on laboratory conditions, newly produced N-type cells have characters such as zero or even negative degradation. So when the purpose of the test is to observe LID performance, the test may be continued beyond 20 kWh per square meter. In the LETID test, the module is exposed to the irradiance of 1000 watts per square meter. Terminate the process after cumulative irradiation reaches about 168 kilowatts per square meter. For PID testing of solar modules, the modules is subjected to a temperature of 85 Celsius degree with around 85% humidity, and under system rated voltage load commonly 1500 volts for a period above 96 hours. The test duration can be extended to 192 hours, 288 hours if more stringent tests are required. In the UV test, the modules is exposed to the UV light within the wavelength of 280 to 400 nanometer, and the radiance should not extend 250 watts. The total UV irradiation should at least 15 kilowatt-hour. For the thermal cycle test, the module should endure two extreme temperature conditions between -40°C and 85°C, and the modules being tested usually undergoes 200 cycles. In the damp heat test, the modules to be tested is placed in a chamber with a certain temperature and a certain humidity. The test duration is basically 1,000 hours and can be extended to certain hours if more stringent tests are required. Mechanical stress sequence is comprised of 4 test protocols in sequence. Static mechanical load, dynamic mechanical load, thermal cycling, and humidity freeze. SML comprises 3 rounds of 1 hour downward force and 1 hour upward force at 2,400 par. And DML comprises 1,000 cycles of oscillating loading at 1,000 par. PV modules are then placed into environmental chambers to undergo 50 thermal cycles, followed by 10 cycles of humidity freeze. All these results conducted by TUV Nord fully verify the high reliability of Jinko Solar's N-type, which has lower LID and LETID than PERC, due to its high efficiency cell technology and high quality N-type silicon wafer, which not only eliminates the LID caused by boron and oxygen complex defects, but also has a higher minority carrier lifetime. About the analysis, firstly, an LID is primarily caused by the interaction of oxygen with boron dopes, and this interaction creates defect in the crystal lattice of the cell, leading to a decrease in performance. N-type cells, on the other hand, do not contain boron as a dopant, making them less susceptible to LID. While the exact mechanism behind LETID are still being studied, it is believed to be related to the formation of defect due to presence of the certain impurities in the crystal lattice of the cell. N-type cells generally have a higher resistance to these impurities, resulting in higher LETID compared to P-type cells. Secondly, compared with EVA encapsulant, POE provides effective electrical isolation between both sides of the solar cells. It has excellent moisture resistance properties, forming an effective barrier against the ingress of moisture into the solar cells. Finally, the results also confirm that N-type modules have excellent agent resistance properties by developing premium quantity of glass POE encapsulant, further enhancing the mechanical property and anti-vapor penetration property. As shown in the left picture, an output energy yield and performance stability comparison study performed on PERC and TOPCon N-type modules was conducted by CPVT. 2 groups of total 20 pieces of bifacial modules of 2 different technologies were selected from Jinko Solar. As shown in the red area of the tables, the average degradation of group 1, TOPCon with fixed axis, and group 2, PERC with fixed axis, is about 0.51% and 1.38% respectively. Light-induced degradation of N-type TOPCon is much less than PERC. And thank you. If you need clarification on any point, you are welcome to send me email.